shit out of them.
There you go. That's the right plan.
And so I was like, all right, I'll be the martyr here.
Yes. When in doubt. All right.
I'll be the martyr.
All right. So anyway, yes. Go ahead.
Luke said he wasn't going to be here.
Luke is not here today.
He just texted me that.
All right. No Luke, no Sierra. How's the test? She felt guilty about it, except I had mistranslated your message.
Yeah,
She
no,
sent me
I was
another one of her
worried
messages
about
in
it.
another language, German, and I misread it. Well, I read it fully thinking I knew it. She was feeling Zorga about the. She was besorgen about the test, and she was. And I read that, and I had the word Sorgen, which is a German for worried, confused with Schulda, which is guilty. And she was feeling guilty about the test, and guilty about her grade. And I was like, oh my God, what has happened? And I was like worried about this, and I got this message. I had like checked my email during the night one night when the kids when the kids were up, and I was like, why is she feeling guilty about the test? What has happened? And I was like, I must be translating this wrong. No, she's worried about it. Okay, there you go. Anyway, so you guys got it all done?
Yeah, I obviously have struggled.
You struggled. I heard that the test might have been harder than I meant.
I think the Bayes theorem actually, like, that was something I did okay with.
Okay.
Yeah.
Well, I'll tell you what. I will pick them up. Here's the deal.
You want the homework?
Okay, let's take the test first, and then I'll pick up the homework. And
Yeah, I did it.
yeah, you guys did it. Okay, here's the deal. I know you guys all got it done in class, and it was just that little thing about averages. And so let me pick these up, and then let me pick up the homework. You guys can work on getting it out. Okay. So you can see, though, where we're going in class right now. We are kind of shifting gears just a little bit. There's lots of classes in college that have names like probability and statistics, okay, or introduction to statistics and probability, or those kinds of things. And page 415. I know you did it. It might even be that you did give it to me already, and it's in my folder, which I did for
I
today.
don't have anything in my notes.
Okay. Here's the deal. If I've lost it, I know everybody got it done or almost done in class. And I'm not expecting, I'm not even sure that I will actually grade these versus look through them and give everybody 100, because I think your ability to compute an average is probably fine, right? Strangely, it's on the checklist of things I'm supposed to verify that you can do, but I'm pretty confident about this one, okay? All right. We're starting to tie this idea of probabilities to statistics. Now, a pair of terms that your book is not using, but which is normally something that is taught at this point, and so I feel like I need to mention this, is there's two different kinds of statistics that we're going to be using. Well, wait a minute. Let's do this in a better way. What are we going to do with this stuff? Malia, what kind of problems, what kind of questions can we answer using statistics? Give me an example of a problem we could answer using statistics. Think of something you could be reading in a class, you could be reading in the newspaper, a kind of problem that we would solve using statistics.
Test grades.
Like the polls.
Polls, like before an election. I like that answer. Okay, so one kind of thing we could be answering about would be something about anticipating what's going on with an election. Does that make sense? Okay. Give me an actual question, Lisa, that you think we could answer using statistics involving polls.
Could you just do like how many people voted for like these people last year? So then likely.
Oh, you're overthinking it.
Oh.
You think it even easier. How about what fraction of voters approve of Proposition 781? And there's no such thing as Proposition 781. But, whatever. Let's say it's legalize something, or it's, change the law about something, okay? But a question we could ask is we could gather data about how people feel about Prop 781, and we could say things like, after that, we could describe what fraction of voters approve of that, right? That is a kind of statistics. where we could be figuring out, we could describe. And there's a reason for that. That is called descriptive statistics. We are describing data. We are describing the results of a sample that we took, a survey or something like that. So we can like say, this many people are approving of Prop 781. Or it varies from county to county how many people approve of Prop 781, from as few as this many to as much as this many. Like the range of rates at which people apply. Okay, it wouldn't have to be as simple as, so this could be things though like average, which we did today. Okay, but there's a whole laundry list more of these kinds of descriptive statistics. And that is a different story than other questions we could answer involving statistics. For example, who texts faster? Men or women? Like, who can actually do that faster? Yeah. I don't know the answer to that. Personally, I found that question a little spooky in a vaguely sexist kind of way, but it was actually the example in one of the lesson plans I was looking at, so what the hell? Somebody else came up with it. Here, this is a tricky question. I mean, it's not hard to just gather data and find out the average rate at which men type texts and the average rate at which women type texts. But here's the deal. That kind of depends on the sample you took, right? I mean, if we all typed, we only have 2 males and 4 females in this room right here. If we did the texting, I'm terrible at texting, I'm terrible at typing on glass. I'm going to be dragging the average down in this group, right? On the other hand, if we took another sample, so like if men text, look, if we did it in this room, and men, the average rate was 12 words per minute, and women, the average rate was 40 words per minute, does that mean that women are faster texters? No, it just means that in this sample they are. But a different sample that doesn't involve an old person like me who's terrible at typing on glass, we'd get a different answer, right?
Are we allowing for the use of emojis in this?
Well, I'm not even going to go there. Plus, even if we had a better sample, let's say it worked out to men typed at 18.2 words per minute and women typed at 18.3 words per minute. Is that actually a big enough difference to conclude that women type faster, or is that just a function of the sample I have now? You know what I'm saying? Or slightly different. If I had sampled another group, maybe men would have been big. Is this big enough that we can consistently say women are faster at texting than men? This is called inferential statistics. Inferential statistics. These are the statistics that we are going to be using to make inferences, or decisions, or to reach conclusions. And we're going to get there. Although, like I said, I don't remember from last year anyway that they actually ever used the word like inferential in descriptive statistics. But this is going to be stuff like z-scores and the bell curve and stuff like that. Where, like, for example, you take some standardized test and you get a score. Well, congratulations, on the WEA5 test you got a 720. What does that even mean? Right? Your parents get the note that you took a standardized test. What the hell does that even mean? Or, well, they then provide them with things like, you scored at this percentile, or you scored higher than this percentage of students. Andrew took the WAK5-3 standardized test and got a 712. What does that even mean? Oh, Andrew scored higher than 98.2% of students. Okay, from that we can make an inference about, is Andrew a better than average student? Yes, he can. We can, right? His parents can reach conclusions about such things. This is called inferential statistics, okay? We have two different medicines to reduce fever. This medicine reduced the fever on average 1.2 degrees. This medicine reduced the fever on average 1.3 degrees. Can we reach a conclusion that the second medicine is better at reducing fever? Your words like statistically significant and so on to determine things like that, okay? We will get to inferential statistics, but today we are still spending more time on descriptive statistics, ways of describing the data. So let's say we have some data. Are any of these pens I have in my pocket any good? Let's try this. Let's have some data. Let's have data. Oh, let's work on this problem about who texts faster, men or women. So I'm going to get some data here, and I'm going to make it in the form of a graph. Where we're collecting data for a number of different people. And we're going to gather how fast they text in words per minute. Okay? We've put a little app on their phone that keeps track of how many words per minute they type. We got their permission to do this, and we have a sample. The lesson plan for today actually said make the students do this. Like give them a paragraph they have to type on their phone without using autocomplete and actually gather information. And I was like, yeah, no, first off, there's only like 5 of us. That's just not gonna, I mean, that's not, if I had a section of this with 60 people, it'd be different, right?
We could do that in pre-cal.
No! We don't do anything in pre-cal that distracts from the main thing.
Yeah.
All right, so let's say, I'm gonna use, just to engage in stereotypes, I'll use blue for boys and red for girls, or pinkish because it's red. All right, and let's say this guy types at this rate. You know, so he's at this speed. We won't worry about what the speed is. And this guy types at this rate, 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 and this guy, woo, look at this guy, he can really go. And this guy types at this rate. Okay? So this we made like a little graph here, right? One person's pretty slow, one person's pretty fast, lots of people are near the middle. And we also gathered data about the girls. And she types at this rate, 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 and she types at this one, and he types at this one, she types at this one, and she types at this one, and she types at this one. All right. So I've made 2 different graphs here. Well, I put 2 different sets of data. How fast the women type and how fast the men type. And I have made it deliberately thinking about some questions I'm going to be asking. But if our core question about it has to do with we want to know more about the rates at which men and women type on their text on their phone, we now have some interesting data to work with. Now, clearly, one piece of information we would want, well, wait a minute, I shouldn't be doing this. Haley should tell me. What is one piece of information we would want if we had data about a whole bunch of different people and how fast they type, and we want to know about the differences between how men type and how women type? What's one piece of information we clearly need from the last lesson?
You know, I actually think that, did you go over 9.1 last class when you
Yeah.
did the test? I wasn't here.
Oh, you weren't there. Okay. That explains it. Yeah, we only did a little bit, like we just did a couple quick problems because we were done reviewing with like 30 minutes left. So we just did a couple quick problems in 9.1. Okay, that explains it. All right, so one quick piece of information. MJ, what clearly do we need to know about these 2 groups from 9.1? Yeah, one thing we need to know is the average for the men and the average for the women, right? Okay, so graphically, the average would just sort of be like a line, right? I mean, here is the average for the men. And here is the average for the women. Okay, we need some notation. When we talk about an average, okay, first off, we have some symbol here what is going to be our symbol for like each person's speed? Well, let's say since I put X's on here, I guess I'll just use, I was thinking of it as just sort of a little marker. Let's say that X is our symbol for like words per minute, then this is X bar for the men. That over bar is the symbol we use for average. And that over here, this is X bar for the women. We are showing the average. Just literally we added them up and divided by how many there were. Just like you did in this 9.1, which was no big deal. I'm so sorry I forgot that you weren't here on that a week ago. You did get the test though and everything, right?
Yeah.
Okay. All right. So real quick, just the average between the two would be a useful piece of information. And clearly in this case, the women are a little bit faster than the men. But it would be very difficult to come to an inference yet that women type faster than men. I mean, if I had pulled this one slowpoke out of here, the average for the men would clearly be quite a bit higher, right? If I had pulled one or two of these fast typers out for the women, like if they hadn't answered the question or hadn't completed the survey or whatever, clearly the women's average would be lower. Clearly, we're still having some trouble making an inference, but we're not on the inferential part of this statistics yet anyway. Lisa, as you look at these graphs, setting aside the average, what's another interesting thing we could say about, say, the men and the women and their speeds here? And you don't have to overthink it or anything. I mean, like, what's another way in which, does everybody type at the mean speed, at the average speed? No. So what's another important thing we need to know about?
They're all different.
How different they are, right? We need to know, just knowing that it works out to 12 words per minute for the men and 13 words per minute for the women isn't all that helpful. I mean, that's good. We need to know that too. But there's other things we need to know. Well, one thing could be damn useful. Andrew, what would be one way, if you needed to tell somebody about this data, you wrote an app that is recording this typing data, and this is the data you got. What could you tell people other than the average? What other another thing you could tell them about it?
Yeah.
Yeah, well, like for example, somebody, you're at a job interview, and you're like, hey, you won't believe this app I wrote. It keeps track of, and I could keep track of like what the average rate at which people were typing.
Like the mean?
Well, okay, what else? How about like, kind of interesting who's the fastest and who's the slowest, right? So the minimum speed or the maximum speed sounds like a useful thing. Cool, cool. Another way to describe that would be the range. Now, range doesn't quite mean what you think it does. I mean, in conversation, if I'm telling you the range on the finite math tests is from 50 to 100, you know what I mean, right? The lowest was like a 50, and the highest was like 100. From a statistics point of view and a math point of view, that isn't what we mean by range. In this context, what we mean by range is the difference between the maximum and the minimum. So the range is just a number. I know that's not how we use it in like day-to-day life, but that is what the statistical definition of range is. So in this case, for the men, we could take the highest and we could take the lowest and take their difference, and we can talk about that there's a range for the men. Now, there is not actually a symbol for range in statistics for whatever reason. We usually just write the word range. Okay? So we can compute the range for the men, and we can compute the range for the women, and that would be okay. That would be a perfectly useful piece of information. It's also a wee bit screwy of a piece of information. For a lot of the same sort of reason, that some other measures can be kind of screwy. I mean, average is kind of dopey in a way. Don't get me wrong, Average is a good measure of the mean. It's not a measure, we talked about this the other day in class a little bit. Remember there was a difference between average and mean. Mean is if we really could measure everybody. Okay, if we measured every male who types on a phone, and every single one, regardless of whether they're on iPhone or Android, whether they're in America, whatever, we could actually have the mean speed at which men type. But that's not really a viable thing, right? We're getting just the average, a sample of the people, right? Here's the deal. What happens to the average if my dad is in the sample too? It's not so great, right? You add one person in there who's terrible at it, and you've dragged the average down, right? Meanwhile, some Instagram influencer, YouTube star, who comes in and she types up here, right? She's just crazy good at that. The thumbs are a blur. She messes with the average too, right? It's not entirely fair that she's in there. She's an outlier. And that hurts the average, right? I mean, it drags the average into ways that aren't entirely representative of the group, right? Average is in some ways kind of a dud. That's why we have other ways of estimating the central tendency too, which can be used in certain cases. For example, median. The median is the middle. If you put them in order, like you sort them, it's the middle one. So if we had 11 people's typing speed, we would put them in order and take the 6th one. Right? So that half of them are slower than this and half of them are faster. That's the median. What if you have an even number? Then you take let's say we had 12 people, then we take the 6th and the 7th, and we take the average of those two. Because again, the idea of median is it's a number where half is slower and half is faster. Or half is the median test score on the ACT, on the SAT is a 910. I don't know what it is. Okay? That means half the people who took it get less than that, and half get better than that. Okay? The advantage of that is these outliers don't screw with the median. If that one YouTube star, Instagram influencer types 200 words per minute, who cares? It doesn't change anything versus she typed 100 words per minute, or she typed, she's just higher than average, right? She's still higher than average, but it doesn't, higher than the median, but it hasn't moved the median at all, right? The middle is still the same person. Same with my dad being in here. If he gets much better, he types like 5 times faster than he used to, but he's still the slowest, right? He'd be changing the average, but he's not changing the median, right? The middle person is still the same. This is an awfully good way to start measuring central tendency if there's outliers. Did I tell you ever about the neighborhood I lived in Omaha when you lived there?
Other than the fact that everyone spoke Czech.
No, that's my hometown when I grew up. No, I grew up in rural northern Nebraska. That's another whole story. No, when I lived in Omaha, I lived, by average, my voting precinct is like the 3rd richest voting precinct in America. Ooh la la! Right? Sounds impressive. You looked at the voting precincts around us and we made way more on average than anybody else. And it's not because I lived in a place fancy. I lived in a perfectly normal 2-bedroom house. Looks just like any house in this neighborhood around here. Why were we so damn rich? Because 3 blocks down from me lived Warren Buffett. Who's Warren Buffett?
One of the richest men alive.
Yeah, he used to be the richest man alive. He's the Oracle of Omaha, behind Berkshire Hathaway. He has over $100 billion. He's one of the main investors behind McDonald's, behind Coca-Cola, behind Geico Insurance, behind whatever. And part of the mystique of him is he lives in like a 3-bedroom house that he bought for $97,000 20 years ago.
Oh, he's that guy.
Yes!
Okay.
It's not because there's anything fancy about our neighborhood, except for the fact that there's a guy who makes who has $100 billion down the road. Right? He in fact also has a home, by the way, in Malibu. So don't feel just too sorry for him. Anyway, but part of the mystique of him is that he lives in a house he paid like $97,000 for.
And like, wasn't that like in the 50s?
Yeah, something like that. Yeah, exactly. I mean, so anyway, so yeah, he lived like 3 blocks from me. Okay, so of course we're totally skewed if you took it the average. Because you add up a whole bunch of people who make perfectly normal amounts of money, and add one person who's got $100 billion, and it kind of messes with the average. Would that have changed the median? Heck no. He's just the outlier then. He's the most. It affects our range, but the median would still be the middle. You know, we line up by income. Warren's on the end. He's on the big end there, right? But it doesn't change who's in the middle, right? The median income in our neighborhood was still, you know, $40,000 or something like that, just like everybody else's neighborhood around us was, right? All right. It's funny because actually in one of the printings of this textbook, they actually used Warren Buffett's zip code as the example. And how random that that's actually where I lived. Anyway, so when I was in college, I lived actually for a while with my aunt and uncle who lived really close to him. They were only like 3 doors down from him.
Did you just casually meet him?
I've never met him. I've met his daughters a couple times. But I've never met him. I mean, he's super old. He's like 90 or something.
Yeah.
I mean, even his daughters are like grandmothers. Yeah. Anyway. Okay, so median is another way of describing this. So you could have the median speed of the men, and you could have the median speed for the women, and so on. That would be another statistic that would describe them. While we're at it, we could talk about the mode. Now the mode isn't really applied very well here when we only had like 10 observations of the men and 10 observations of the women. It would work better if we had lots of observations. Where instead of me just making a little graph here that had little markers indicating how fast each person was, if instead we had something like a histogram. Where like I had speed over here on the x-axis and like the number of times we observed that speed over here. And like there were a few men who were very slow, and some that were a little faster, and some that were a little faster, and some that were this speed, and some that were this speed. Right? This speed was observed a whole bunch of times. This other speed was observed half as many times. Maybe this, and then this, and then this, and then this, and then maybe there's somebody over here who's really fast. Right? I don't think we have to get too bogged down in histograms. I think the idea of like it's a bar graph that shows how often this speed, let's say this is 20 words per minute, that was the most common speed. 40 was a rare speed. 2 was a rare speed, right? The mode is just the tallest bar on a histogram. It's telling you what's the most common thing. And that too can be kind of what we mean. Remember, all of these things, median, average, and mode, are all ways of kind of estimating what we mean when we talk about central tendency. Because that's really what we mean, right? We kind of mean where's the middle of this, right? And as long as the distribution is sort of mound-shaped, bell-shaped, you know, there's a bunch near the middle and then it gets rarer toward the end. Things like mode are pretty good ways of getting a sense of what is the central tendency. So mode, median, and average would all be good estimators of central tendency. Which is something like mean. Did we use that symbol lowercase mu for mean the other day?
No.
Okay. The right mathematical symbol for mean is a lowercase mu.
Good estimators of mean.
Central tendency. I'm sorry that my penmanship got kind of bad there. Central tendency. Central tendency is kind of an undefined term. It's the kind of thing we know what it is without actually having a good definition, right? We mean what's the middle, where is most of it. Central tendency is something kind of an abstract idea. Mean is specifically like average if you had everybody. And remember, as we talked about a week ago, mean is something you can't actually know. We did the example about the heights of the kindergartners, right? If we had some commission to find out the height of all the kindergartners, how do you even do that? On any given day, I mean, you could make a plan that you're going to go measure every kindergartner, but how does that even work? Because they're not all there that day. And besides, if you didn't get to them, what about the ones you got to come back and measure them? Well, they've grown since then. It's not really something you can know. It's a real number. There really is some mean height of the kindergartners. It's just basically impossible to get to it. But we can estimate it by grabbing 100 kindergartners and measuring them and taking their average. Or getting 100 kindergartners, lining them up and finding the middle one, finding the median. We wouldn't really line them up and measure them. I mean, but you know what I'm saying? You'd measure them and then sort the numbers or something like that, right? Or mode. You know, there's some real short kindergartners and there's some really tall kindergartners, but there's a middle height there someplace that most of them are, you know, right around maybe 36 inches or something like that, right? So these that I've drawn a box around, those are all estimators of the central tendency. They are descriptive statistics that are helping us know something about the middle, the central part of this data. But range was different. Range was telling us about ways in which individual observations were different from the central tendency. It was a measure of how things could be different. And what we felt was, you know, before I had my dad over here, and before I had some YouTube star over here, the way I had them drawn, you can see I kind of deliberately kind of did something.
You just assume.
I kind of made it so that the range was the same for the men and the range was the same for the women. Do you see how I did that on there? They both had a range of about the same amount. But I'm not sure that necessarily tells us all that much here. I mean, notice the way the men are distributed and the way the women are different, the men's scores are distributed and the way the women's scores are distributed is actually quite different. Did you notice how the men are all kind of clustered right around the average except for the few who are weird? And the women were kind of more spread out, right? They ended up having the same range, but they're clearly somehow different. There needs to be some way of describing how scattered out they are. How close are they really to the average? Right? I mean, it is altogether different to know two different schools have the same average SAT scores, but to know that this school, they all kind of fell near the average, and this school has a very wide distribution, where like there's really good high-scoring students and students who are really struggling on that test, right? Those are two different pieces of information. We need some way of figuring out how to get to that. How are we going to start understanding how spread out the observations are? Okay. Well, as sort of a little gateway to that, I'm going to show you something graphically on here. Every one of these observations that we took on here is different from the average. Not even one of them happens to be exactly on the average, the way I have it drawn on here, right? Some of them are pretty damn close, but none of them are exact. I guess some of them could have been, but it didn't. All of them are a little different. There is some difference between this observation and the average. There is some difference between this observation and the average. There's some between this one, and there's some between this one. And in fact, every single observation on here is in some way different from the average. Some are very different from the average, and some are not all that different from the average, but there's some distance between the average and the observation. And in fact, that we could come up with a way of talking about that. I mean, if I numbered these observations, here's observation 1, 2, 3, 4, 5, 6, 7, 8. Any given observation that I have on here has some difference between it and the average. In other words, the length of this stick that I drew here is just that observation minus its average, minus the average of its group, of its cohort, to use the right word. like a useful piece of information, right? If this wasn't typing, if this is typing speeds, this is telling you how much slower or faster you are than the group. This guy, his number here is going to be negative because his observation is slower than the mean, so than the average. So his observation minus the average is going to be a negative number. This person's is going to be really small. This one's a small negative number. This one, just let me use him as another example, is big and positive. We need a word for these guys. I don't know if your book actually used a word. Sometimes these things are called deviations. Sometimes these things are called anomalies. In science, we usually call these things anomalies. The difference between an individual observation and its group's average. Sometimes that's called errors, but error is kind of a judgmental word. Doesn't it sound like it's getting a little judgy on you? Like if we said that those are errors, it's not an error, but that is often the word we use. You may have heard terms like mean square error and crap like that, like in the science class or something like that. Okay, it doesn't mean error like you've done something wrong. It just means error in the sense of ways in which it's different from its average. I like the word anomaly best, but that's because I come from science, and scientists tend to use the word anomaly. Can we agree? No. MJ will tell us, use some words, MJ, to tell me ways in which the anomalies for the girls are different from the anomalies for the boys. Like, when you look at the anomalies for the girls and their typing speed, how are their anomalies different than the anomalies for the boys?
Their anomalies are, one, there's a lot more of them, and two, they're at varying stages. Like, if you look at the guys and stuff, there's really only two. There's like your dad.
I don't remember. Somebody over here,
Or
yeah.
is it the slow person, the fast person, and that's pretty much it for the guys. But then you go over to the girls, and it's like there's like one a little bit down there, and then there's one way down there, and you got one that's way up there, and you got a couple that are like somewhat down, and a couple that are somewhat up. It's all over the place over there, so there's a lot more anomalies.
I like her answer so very much. Can we agree that the anomalies, the length of those sticks that I drew there, are different for the girls than the boys? And it seems like generally in this case they're longer, right? The anomalies for the boys are shorter, and the anomalies for the girls are generally longer. Now, Mr. Andrew, if I wanted some kind of number to say, look, overall the girls' anomalies look bigger than the boys' anomalies, what do you think we could do with that? What could we do to describe how her numbers, the girls' numbers are different than the boys' numbers? What could we do about the lengths of those sticks to describe how they're generally longer over here or they're generally shorter over here?
Say maybe they have a different method of typing, or
No, I mean like how could we know, and in terms, I like your answer, but I mean like in terms of like what could we do to describe that? Like what kind of number could we give?
like how many outliers there are.
Well, how many? That's a good way of doing it. I hadn't thought about that. How about we just say the average length of those sticks? Right? The average anomaly. Does that make sense? I mean, would you agree that the average length of them over there for the girls is different than the average length of the boys? Oh, there's, right? Sounds great. Except for one thing. Malia, can you anticipate why that's not going to work? I think, here, I'm going to give you another symbol. The symbol for these anomalies or deviations is a tick mark. So like x1 with a tick mark, x1 prime, means like this difference. So like this one, here's an x5 prime, this thing up here is x7 prime, etc. Can you see what's going to go wrong with this, Malia? If I try to take the average of that. If I tried to say, hey, one way to describe this would be to add up all of these anomalies and divide by how many I've got, like an average anomaly, what's going to happen?
Is it because like some of the anomalies are negative?
Yes! In fact, half of them are, right? In fact, if you add up all the anomalies, we're not going to prove that to you, but in a stats class you would, it's 0. If you add up this negative number, this small number, this small negative number, this small positive number, this big, if you add it up, it's 0. Yeah, we got a problem here. seems like the average length of these things is something we mean as a way of describing, are we clustered near the mean or are we spread out? But just adding up the anomalies divided by how, like the average length of an, here I'll even write that down. Average anomaly sounds like it would be a good idea. It would be a way of describing how scattered they are, except it doesn't work. Because when you add up the anomalies, you get 0. Because, as Malia said, some are positive and some are negative. Whatever could we do about that?
Make the negative ones, add them, put them in as a positive.
Yeah, okay. One way to do that would be to say, I don't mean here, let's even write this down as an equation over here. We had been making this as like, we add up all the anomalies and divide by how many there are. And Malia says, well, what about make them just like absolute value? Right? I mean, I guess we could have something that's like average absolute anomaly. Or average absolute deviation or something like that. Where we'd be like summing up the absolute value of the anomaly and dividing by how many we had. Does that make sense? Like that seemed like that would work, right? And it would. And in fact, that is a type of statistics. But it turns out that that does not have ideal properties. It turns out there's a lot of things we want to be able to do with these statistics, like to have a sense of how big their errors are and so on. And it turns out that absolute value is kind of a mess. Okay? It turns out that's not... You might even have chest pains remembering the days in classes like pre-calc. Whenever there was some damn equation that's got some absolute values in it, what a pain in the butt it was to graph the damn thing, what a damn pain in the butt it was to do it on your calculator or in Desmos or however you were doing things. Remember, absolute value makes things a mess. It's actually hard to do any kind of proofs using it, it's hard to... So here's the deal. There are other ways, though, we could do. There are other things we could do to these anomalies that would guarantee that even if they were a negative number, we could treat them like a positive number. What is another thing you could do to a negative number that always turns it into a positive number? What could you do other than that?
Multiply it by -1.
Well, but then if you have a... Okay, how about this? What is something you could do to any number? What is a function you can do to any number, whether it's positive or negative, but when you're done, it's a positive number? What always results in a positive number? Squared! Squared always takes, it doesn't matter whether you're taking -4 or 4, squared is 16. Right? That always changes it. So what if I had like, I'm going to just sort of punt here and call it average squared anomaly. So in other words, I mean something like sum up all of the anomalies squared and divide by n. Now that sounds like that would work. So I take each of these anomalies, square it, add them up, and divide by how many there are. That sounds like that would work. Then the places where the anomaly is negative and the places where the anomalies are positive, it all adds up. Now, and we are real close to the idea here.
What is the bottom end that you're...
I'm sorry. Let me make this a capital N or something like that. Like this is how many we have. Okay? Maybe this little n here should be like I or something instead. Does that help? Like we're just sort of counting through. Right? We mean like x1 anomaly squared. This x2 anomaly squared. This x3's anomaly squared, and so on. And we are really damn close. Hold on. Yep. Hold on. This is pretty damn close to a really good way of describing the data. There is one little theoretical problem. I don't want to get bogged down on it. But can we agree that this is really damn close to doing the same thing where we would be adding up all of the anomalies, squaring them as we go, and dividing by n minus 1 instead? Okay? As long as n's a biggish number, dividing by n and dividing by n minus 1 is basically the same thing, right? If n was 300 people's typing score, is dividing by 300 and dividing by 299 all that different of a thing? It actually doesn't change the number. In fact, as long as n is bigger, it can be shown, is bigger than about 30, this won't change the number all that much. Okay? There's a good theoretical reason why it has to be n minus 1 rather than n here. But this turns out to be an important descriptive statistic called the variance. The variance is a nice measure of how spread out the observations are. The bigger the variance is, the more spread out they are. And the smaller the variance is, the more they tend to be clustered around the average.
How spread out like the anomalies are?
Yes. Yeah. The observations are mostly close to the mean. You'll have a small variance. The observations are mostly kind of farish from the mean. Will be a bigger variance. But notice I'm being a little loosey-goosey here. I'm using words like bigger and smaller. How big? How small? Well, there's another little ugly thing too. Our observations were in words per minute. Our average was in words per minute. Each person's anomaly or deviation is in words per minute. Yeah. We're just going to be talking about units.
Oh, okay. I already got all those ones.
Okay. Words per minute, when you're talking about studying typing speed, sounds like a damn good unit, right? Being able to say this guy types 10 words per minute slower than the average is a useful thing. Saying that the average is 20 words per minute sounds like a useful thing. Hey, what's our units of our variance? Well, let's see. We took the anomalies, which were in words per minute, and we squared them. So now our units are words squared per minute squared. What the hell is that? What the hell is a word squared per minute squared? I mean, variance is a perfectly good way of describing data, but the units get screwy. Because they are whatever you've been measuring squared. So if we've been measuring typing speed, the units of variance are words squared per minute squared. If we have been measuring temperature in Evansville on November 14th, and there's some cold days and some warm days, and we're doing this here, our average has units of degrees Fahrenheit. Each individual year's observations have units of degrees Fahrenheit. And our variance has units of degrees Fahrenheit squared. What the hell is a degree Fahrenheit squared? So even though variance is a perfectly good way to describe things in terms of how the data are spread out, the units kind of don't make a lot of sense. So we need something better than that. But you know what? The only problem here is really that this whole idea that the units are squared. In fact, it seems like if we just put a big old square root sign around the whole thing, we'd have solved the problem. And in fact, we could do that. A big old square root sign around the whole damn thing, where we just added up all the anomalies, squaring them as we go, and divided by how many there are, sounds cool. Because now, if variance had units of words squared per minute squared, now, taking the square root, it just has units again of words per minute. And that is a nifty thing called the standard deviation. The standard deviation is another way of describing how scattered the observations are. If the standard deviation is small, they're mostly clustered near the average. If the standard deviation is big, they're mostly scattered far away from the average. There are, just like there was symbols for average and mean and things like that, there are symbols for standard deviation and standard deviation and variance. The symbol for standard deviation is either an S, it's lowercase s, or a lowercase sigma. There are slight differences as to why you would use one versus the other. I think the book always uses the S.
Sigma?
It's a lowercase sigma. If you don't know your Greek letters, a lowercase sigma is sort of a little circly, triangle-y thing. I usually draw it this way, and I was trying to be a little more accurate with it. It's sort of a circly thing with a tail. So the symbol for standard deviation is either lowercase s or lowercase sigma. And the symbol for variance is either s squared or sigma squared. In other words, even in our idea of what variance means, we already have hidden the fact that we're really going to move on and do standard deviation. Standard deviation, then, is a measure of how scattered the observations are. Your book doesn't show you this yet, but I think it's useful to understand what standard deviation is. Let's say we made ourselves like a bell. We are actually making ourselves a curve, like a histogram, that shows speed over here and like how many times you observe that over here. And we've already said it should kind of look like a bell curve. It should kind of look like a normal distribution. We should have a few people who type really slow, a bunch of people who type faster, and then a few people who type really fast. Right? We would expect it to have that kind of normal distribution where like the average is about here. A standard deviation is how far you need to go to where the curve kind of bends, where it inflects. See, before it was turning down and then it kind of starts turning outward. One standard deviation below and one standard deviation above is how far you need to go. So one standard deviation above and below is kind of like the hump of the distribution. It contains the bulk of them. It contains 68%, by the way. Well, we aren't there yet. But if you actually like plotted how fast each person went, you know, it's like where the distribution starts to curve. But it gives you a sense because it could have been different. Maybe men typed like that and women typed more like, you know, their curve was more like this. Okay? They had a slightly higher average, but their standard deviation was much bigger. They had a wider range to their bell curve. It took farther before they got to where the curve is turning outward and, you know, kind of inflects like that. All right, now, I forgot to log in, so I'm going to try to do this here. And that's what's going to be on the test. No. All right, so for today, and because I didn't log in, let me try to get this on my phone real quick. You have an assignment that just gets some exercise plotting these things, calculating these things. Come back here. In Finite Math on the lesson plan. Where's the lesson plan? Lesson plan for Finite Math. So we're going to do a little bit of stuff on 9.1 and then a little bit of stuff on the last one. I mean, on 9.2 rather. Hold on. This document is too long for my phone to be happy with. Hey. Alright, I will have to log in. Alright, hold on. It is logged. And there is a little exit ticket for today. In fact, I'm going to give you the exit ticket first because some of the problems involve a little thinking. is not posted yet, so hold on. There is just too many things going on today.
Is it because you have to play secretary, principal?
I have to play all my roles today. All right, so it is now available to you. It's like 10 multiple choice questions about statistics.
It's like you're wearing different hats. But
I kind of am. And
instead of switching them out, though, you just keep stacking them.
that's actually not a bad idea. Here's the finite math lesson plan. Just soon should be able to jump all the way to the end. And there it is. Okay. So for today, some of your assignment is on page 416, and it is you'll do number 36 and 37, and on these, just do the median. It asked you a couple of questions about other things. In fact, I think you might have done this one as one of your averages, but on that, you just do the median. And then on, let's see, 30, and you also do 38B, and you also do 44C and 44F. And then that's all stuff from section 9.1, and then 9.2, you do page 425. And it is 3 through 8 and 25 to 27. All right. And then, before it gets any later, let's...
So wait, 38B, 44C, and 44F are what?
They're in that page 416.